All right, so starting with number 5. Part of this mass was this on a purchase. Remember, if you don't need this one, feel free to work on another one, but please don't be a distraction. Thank you. This card, the same cards stick together after the collision. So what type of collision is this if they stick together afterwards? How do we categorize it? Not only inelastic, but perfectly inelastic. So that's probably where I'm going to start my Y. Go here, and I'm going to do a little typing. I'm going to start with this. It is a perfectly inelastic collision. Thus, the momentum is conserved, but the kinetic energy will be less after the collision. Let's see if there's anything else. Initial kinetic energy, final kinetic energy of the system. All right. So I'm expecting a bigger answer for A than for B. Let's see. So I need to do my diagrams now. Oh, I should probably mention the impulses, right? I can either draw them in or I can draw them. So or mention them. So the carts undergo equal but opposite impulses when their momentums change. It's always weird when words aren't in spell check, like momentums is not. That's weird. Alright, so that's probably all the writing part that I need to do for this one. Now I need to do my drawing. So we'll have first card. Do they number them, letter them? Let's see, what do they do? What do you want to call them? Cart what and what? A and B? Okay. So this is cart A, and then this is cart B. This would be the momentum of A and the momentum of B. Because it's sitting there, I know is 0. Right? And then afterwards, I've got one big cart AB. And it's going to have momentum AB. I could actually add my impulses in there and say the impulse on B equal and opposite to the impulse on A. I don't like to build problems. Alright, so I could draw those in there. But yeah, I would do it for the Y. Good? And I think we hit all our rubric points there too. So I'm going to need some equations. So, grab my equation sheet. Definitely going to need this one, which is for momentum, right? So, let's put that one in there. And since the problem is about kinetic energy, I'm going to go out on a limb and think I need the kinetic energy equation. And we'll just put those up there. Alright? So I'm interested in the kinetic energy before and after. To know kinetic energy, I need to know the mass and the speed. I know the masses, but I only know I know the speed before, but I don't know the speed afterwards. All right, so I don't know what happens with the kinetic energy, so I can't directly use kinetic energy to find out the kinetic energy. I need to use the fact that momentum is conserved, and then that'll help me get at the kinetic energy. So I'm going to start off with what my diagram tells me for the y is that the momentum before equals the momentum after. So the momentum of A plus the momentum of B equals the momentum of AB, because momentum is conserved. And so my diagram directly gives me my first equation, which is momentum of A, which is a vector, plus momentum of B, which is a vector, equals the momentum of AB, which you guessed it, is a vector. And now I can substitute in mass of A, the velocity of A, plus, what's the momentum of B before the collision? 0. Equals, this is the mass of A plus the mass of B, whatever velocity AB has. Now I've got to keep in mind that these are based on velocity, where kinetic energy is based on speed. So it's important that especially in other ones, that I recognize that. So now I can solve. I can put in and solve, right? 0.12, identical cart, 0.45. So this is 0.12 kilograms, moving at 0.45 meters per second. Equals 0.12 kilograms plus 0.12 kilograms. I bet it's going to be, I bet my answer is 22.5. Because I looked at it, my mass doubled, so my velocity is going to drop in half. So now I need, but that's not what they want to know. They want to know what's the initial kinetic energy and what's the final kinetic energy. So we need to use our kinetic energy and look at it beforehand. So kinetic energy before anything happens is going to be the kinetic energy of A plus the kinetic energy of B. I can probably, we'll label that B. 4. All right, now I know everything to substitute in there, and I can find it, right? So then I move on to the kinetic energy after. That's just the kinetic energy of object AB. And it's being weird. Alright, and so using my kinetic energy formula, I can substitute in, right? And get what it is afterwards. Because now I know the speed of it after. So I'll just substitute in, remember it's the mass of AB. Alright, on to number 3. What type of collision do we have? We have an explosion. We have an explosion. It's one of our excellent. So we know, and that's where I'm going to start, is that this is an explosion. So the momentum is conserved, but the kinetic energy increases during the collision. See, the egg rests before the explosion. The egg has a momentum of 0 before the explosion. And the impulses on the parts of the egg will be equal, opposite in direction. Yeah, I think that's everything. Now I get to do my drawing. So, egg, broken egg, momentum of the egg, 0. Do they name the pieces? A and B. So this would be the momentum of A in that direction. That's the momentum of B in that direction. And we could go in here and do our impulses. Impulse on B from A equals the impulse on A from B. Just indicating those are equal but opposite impulses. That might be good to put up here in my Y. You know, I hadn't thought about that, but I think it is a good idea. The impulses create the change in momentum. That's probably a good thing to have in there. Alright. I'm going to grab this rather than, oh, this is 3. So, again, I start with, let's make sure what they're asking. Magnitude of the momentum of piece A before the explosion. Huh. Well, what's the magnitude of the whole thing before the explosion? 0. And they're one object, so 0. Yay. You can answer that one. And then, using component of the momentum of piece B is measured at positive 500 after the explosion. Finding component of A, piece A after the explosion. Alright, so they want to know the momentum of A after the explosion. So, let's see. We know that the momentum of AB, or the, I call that the exit knife. A before equals the momentum of A plus the momentum of B. Right? And those are vectors. That's why that's important. So, they told us momentum of A before was 0. And then they tell us the momentum of B is positive 500. So I don't know the momentum of A, but I want to. Plus a 500 kilogram meters per second. And I bet you can find the momentum of A from that. Right? Alright, so number 7. Brittany stands the rest on a skateboard. As soon as you hear someone on a skateboard, think, oh, they're just getting rid of friction. Or rollerblades or ice skates, things like that. They're telling you, don't worry about their connection with the earth. Isolate them. Brittany's skateboard is 65, tosses a 3.7 pumpkin to Brittany. When she catches it, she and the skateboard begin to roll backwards with the speed of this. What was the speed of the pumpkin? Alrighty. So what type of collision do we have here? She catches it and holds on to it. Perfectly inelastic. Excellent. Yep. So that's where I'm going to start. This is a perfectly inelastic collision. Thus, the momentum is conserved, and they form a single object. Action. All right, let's draw. Now, don't be intimidated if you can't draw her on the skateboard as well as I just did. All right? I don't want you to feel bad about yourself.
Where is she? That's not a person.
Don't body shame her. She looks fine there.
Do not.
Okay. Okay. But she's very nice.
I love her.
Let's see, let me make sure I understand the problem. She stands at rest. Dave, the nasty boy, throws a pumpkin, and they roll backwards. Okay. So, momentum of Brittany, I'm going to say 0. I give the pumpkin momentum that way. And then afterwards, we have the momentum of Brittany pumpkin. Which way should we call positive?
I said right, but probably not.
Okay, we can say right. Now, the only downside I see to saying right, that means every velocity we have is going to be negative. So we got to keep track of those negative signs.
Oh, right.
But we can do that.
Wait, let's do that.
Well, the way my drawing is.
Let's do it by the way.
I hate negative numbers too. I know. I'm trying to be positive. You want to be negative. No. So we're going to call that direction positive. Good?
Great. Wonderful.
Wonderful. All right. I wonder. Oh. I still have it in the clipboard. All right, the equation I'm going to write comes directly from my drawing, right? I got the momentum of Brittany plus the momentum of the pumpkin, both those being vectors, equals momentum of Brittany pumpkin. Vector. And I think they want to know the speed of the pumpkin, right?
Yeah.
They tell me her mass and the pumpkin's mass and their combined speed afterwards. So, mass of Brittany. Oh, wait a minute. How fast is Brittany moving at the beginning? What's her momentum at the beginning? 0, right? She's sitting there. Now I'm right there. Plus mass of the pumpkin, velocity of the pumpkin beforehand equals mass of Brittany plus mass of the pumpkin, velocity of Brittany pumpkin. And they told me all these values. They told me the mass of the pumpkin, they told me the mass of Brittany, they told me the velocity of Brittany and the pumpkin. Plug it in and do I expect it to be higher or lower than that 0.26? Higher. Higher, because that's them moving together and she has more mass in the pumpkin. Good. All right, I will save and post